Okay, hello. Let me introduce myself. My name is Calvin with student ID 136180040. Now I'm going to present my mission reconstruction of Mars Reconnaissance Orbiter, or in short, MRO. Here is the general layout of my presentation. Now I'm going to describe the general information of the mission itself. The Mars Reconnaissance Orbiter mission is operated by the National Aeronautics and Space Administration, or NASA. Its mission is mainly to research of Mars from a low orbit, and it has two categories such as formal science, which does mapping, identification, and monitoring aspects of Mars, such as rocks, layers, minerals, and also the atmosphere itself. And also it has mission support, which relays information from ground missions to Earth and also survey potential landing sites for future ground missions. The MRO is launched on 12th of August 2005 at 11:43 Universal Standard Time at the Cape Canaveral Air Force Station, PAT LC-41, with the coordinates as stated in the slide. It is launched from the Atlas V41 rocket and arrived at Mars on the 10th of March 2006, 21:24 Universal Standard Time. It mainly has 9 mission phases, in which it starts from the launch into a parking orbit, it will stay there for around 33 minutes, and then it will accelerate itself into a hyperbolic escape into a heliocentric trajectory on its cruise phase to Mars. It arrives at Mars at a hyperbolic arrival, and then it will decelerate itself to form a highly elliptical initial orbit, in which then the satellite will perform error braking to reduce that highly elliptical orbit to a nearly circular one, which then it will begin its science phase for around 2 years, with the timeline as follows, and its relay phase, which also be conducted around for 2 years, which with the timeline as follows, and then its mission will be done and will be fired off into into a higher orbit, in which it will remain there for decades to come. Okay, next I will discuss about the launch phase of the mission. Uh, First is about the launch vehicle. The M also uses the launch vehicle, the Atlas V401 rocket, which has two stages. The first one is the common core booster, with the data as follows. And the second stage is the Centaur single engine, with the data as follows. The launch vehicle also has a payload fairing, and also the payload itself, the Mars Reconnaissance Orbiter, which has the data of mass and specific impulse as follows. Alright, next, to obtain the parking orbit parameters, first the left-hand table is the obtained parameters from sources, and to calculate the rest of the parameters, the following calculations are done. The first one is the semi-major axis, which is the average of the pericenter distance and the apocenter distance. While to obtain the eccentricity of the parking orbit, then the orbit trajectory equation is used with theta equals 0, and to obtain the semi-litho's rectum, the orbit trajectory equation is also used, but with theta equal to 90 degree. While the period of the parking orbit will use the third law, the Kepler's third law, to obtain around 87.82 minutes. Next, I will discuss about the launch timeline, which begins on phase 1, which is the countdown and system checks, and followed by stage 2, which is the lift-off with stage 1, which is the common core booster, with a burn time of 4 minutes, and after this, the supposed velocity is around 4.5 kilometers per second. Next is phase 3, which is the stage 1 booster engine cutoff, and then phase 4 is jettison of the stage 1 booster. It means the stage 1 booster separates itself from the rest of the rocket. Phase 5 is the Centaur stage 2 main engine start, and then phase 6 is the first burn of the Centaur stage 2 rocket. which has an approximate burn time of 9 minutes and 35 seconds. While in the first burn of Centaur Stage 2 engine, there will be the jettison of the payload fairing, which is followed by the main engine cutoff of the Centaur after the 9 minutes and 35 seconds are up. Then the remaining launch vehicle will be at a parking orbit, which will have a parking time for around 33 minutes, in which then will begin its second burn for 5 minutes and 29 seconds. After that, the main engine is cut off, and then jettison of the Centaur with the Mars Reconnaissance orbiter, in which will have a velocity around 11 kilometers per second. Then the remaining launch vehicle will also undergo a collision avoidance maneuver to avoid the collision with the MRO or even Mars. Next is the launch azimuth angle reconstruction by using the following formula. Then by plugging in the numbers, it is obtained that the azimuth angle is either 88.92 degrees or 91.08 degrees, which then comparing it to the real mission data with azimuth angle of 93.5 degrees, there is a slight difference which have possible causes of weather conditions, simplification of the analytical solutions because it comes from the geometry, and the neglectment of external forces and moments, which could lead to reconsiderations in the real mission. Okay, next I will discuss about the first approach of the velocity data reconstruction, which is to obtain the parking orbit velocity using 2D problem equations. There are some assumptions, which are the Centaur's second burn will be done at the parking orbit pericenter, and then there will be instant velocity change to enter the parking orbit, and then the drag and Earth's gravitation will not influence the parking orbit trajectory. And using the Kepler's equation for elliptical orbits, we can determine the position of the parking orbit entry by first obtaining the variable t, which is the period minus the parking time, which is 33 minutes, and then by substituting it to the Kepler's equation, we can obtain E, which is the eccentric anomaly, and then relating it to the true anomaly, we get the true anomaly value of 234.5 degrees. And substituting the obtained data into the orbit trajectory equation, will obtain the orbit parking entry distance of around 6,557.6 kilometers. Then to obtain the velocity needed at that parking orbit position, then we can use the Fish-Phi integral to obtain a velocity of 7.788 kilometers per second. Next, I will discuss about the second approach of the velocity data reconstruction, which is to obtain the launch phase velocities using Tsiolkovsky's rocket equation. There are 4 assumptions to this, which is the first, the geopotential gravitation is 9.81 meter per second square. The specific impulse data is at vacuum condition. The neglement of the maneuvers of the launch vehicle, and then the uses of Centaur's stage 2 fuels is linearly proportional to its burn time. Alright, the Tsiolkovsky's rocket equation is used to obtain the velocity change after each burn in the launch phase, and we'll need to calculate each phase's total mass and fuel mass. Now, from the common booster burn, there will be a velocity change of 5.22 kilometers per second, and using a similar procedure, the velocity change of the Centaur's first burn is around 2.94 kilometers per second, uh, while for its second burn will result in a velocity change of around 4.56 kilometers per second. After obtaining the velocity changes, then the velocity after each burn can be calculated as stated in the slide, and will be compared to the real mission or analytical data. A margin is obtained when the values from Tsiolkovsky's rocket equation and the comparison data, which can be caused by the reverse specific impulse uses the vacuum condition, which can be set to represent the actual condition. Also, the burn is not impulsive and has a window of time. Then the negation of drag and maneuvers will directly or indirectly result in more thrust that will increase the velocity of the launch vehicle, which explains why the analytical data velocities has higher values. Next, to reconstruct the heliocentric trajectory, then it is first needed to obtain the Sun's, Earth's, and Mars's orbit parameters, well, except for the Sun, as it will be considered as the focal point of the orbits. The table depicts the obtained data from sources, and to obtain the rest of the parameters, then the following procedures are done. As the semi-major axis and eccentricity of each planet's orbits are already known, then each of the planet's pericenter and apocenter can be calculated using the orbit trajectory equation, with theta equals 0 degrees for the pericenter and theta equals 180 degrees for the apocenter. The period is calculated using Kepler's third law, while the sphere of influence radius is calculated using the formula as stated in the slide. To reconstruct the heliocentric trajectory, then some assumptions are implemented. The first one is the calculation will be considered a 2D problem, which means that all of the object will be considered to reside on a single plane for the calculation. The second is the shape of the heliocentric trajectory, which is considered to be elliptical. The third one is that the altitude of the satellite is neglected as it is small and will not contribute much in the calculation. This will simplify the calculation. The fourth one is that the MRO will not undergo any trajectory correction maneuvers, so it will stay only in one orbit as it is cruising to Mars. And for the fifth one is the effect of each planet's sphere of influence are neglected. After the assumptions, then it is needed to calculate the initial known data. From the graph, the data of theta of each planet in its orbit at the time of escape and arrival of the MRO can be obtained. Then, using the orbit trajectory equation, the orbital distances can be obtained and is compiled in the table. Then, theta heliocentric is defined as the angle of Earth when the MRO escapes Earth's orbit, and Mars when the MRO arrives at its orbit. And then, using the orbit trajectory equation, equations A and B can be obtained, which will be used to calculate the semi-major axis and eccentricity of the heliocentric trajectory by simultaneously solving the two equations. Then, to calculate the transfer time, Kepler's third law will first be implemented to calculate the period of the heliocentric trajectory, followed by the eccentric anomaly from its relation to the true anomaly. After that, Kepler's law is used to calculate the transfer time, which yields around 213.5 days, and compared to the real transfer time of 211 days. This slight error can be caused by using the 2B problem assumption, as each planet has their own inclination. The second possibility is that the start of the transfer may not be the pericenter of the heliocentric trajectory, which can yield different results. And the third possibility is that the real MRO mission has trajectory correction maneuvers, which will result in deviation from its original transfer trajectory, and which would explain the difference in transfer time. As the heliocentric trajectory is already reconstructed, then the next step is to reconstruct the hyperbolic escape trajectory. And like every calculation, some assumptions are made, such that the MRO escapes exactly at the pericenter of the parking orbit, Also, the drag and Earth's gravitation will not influence the trajectory shape, as it will add a layer of complexity to the problem. Okay, first the calculation of excess velocity is needed, and will be calculated using the equation that states that the absolute velocity of the MRO with respect to the Sun is the sum of the absolute velocity of the Earth with respect to the Sun and the excess velocity. As the semi-major axis and eccentricity of the heliocentric trajectory is already known, then using the Visify integral, the absolute velocity components in radial and tangential direction can be obtained for both the MRO and the Earth with respect to the Sun. After that, by calculating the difference of the two absolute velocities in vector form, will yield the excess velocity also in vector form. Then by calculating its magnitude from the vector form, the excess velocity can be obtained, which yields to around 3.61 km per second. The excess velocity can be used to calculate the characteristic energy, which is defined as the square of the excess velocity, and it can also be used to calculate the hyperbolic escape trajectory semi-major axis by plugging it into the Visify integral. After obtaining the required orbital parameters, then to calculate the change in velocity needed to change the parking orbit into a hyperbolic orbit, then it can be done by finding the difference between the hyperbolic orbit velocity and the elliptical orbit velocity, both at the pericenter. And it is obtained that the change of velocity needed is around 3.80 km per second. Then by using the change of velocity and Tsiolkovsky's rocket equation, the fuel needed for the orbit change can also be obtained to be around 5,743.9 kilograms. And by comparing some of the obtained variables, such as the characteristic energy velocity at the hyperbolic orbit pericenter and fuel needed for the orbit change, it can be seen that the analytical values have some deviations from its real mission data. The difference in characteristic energy and hyperbolic velocity at the pericenter can be caused by, first, is that the point where MRO escapes Earth may not be the pericenter. The second is that the negligence of drag and maneuvers of the spacecraft. And the third is that the calculations are using two-body problem equations that neglects the influence of other objects in space, in which is not the case in the real mission. Meanwhile, from the deviation of fuel mass value can be caused by the uses of impulse data, which is referred in the vacuum condition, the assumption of impulsive burn, and the neglectment of drag and maneuvers of the spacecraft, which can yield to higher fuel consumption. For the reconstruction of the hyperbolic arrival trajectory, a similar procedure such as that of the hyperbolic escape trajectory can be implemented. But first, the definitions of assumptions used for the reconstructions are defined, such as that the MRO arrives at the pericenter of the initial Mars elliptic orbit. The second one is that the pericenter of the initial Mars elliptic orbit is radial with respect to the Sun. The third one is that the drag and Mars gravitation will not influence the trajectory. The fourth one is that the MRO will only do one burn to reduce its velocity to enter its initial Mars orbit. And the fifth one is that the effect of Mars's sphere of influence are neglected. But first, an extra step is needed, which is the calculation of the MRO's initial Mars elliptic orbit, in which initially is known the data of the pericenter distance and its orbit period. With that, the semi-major axis can be calculated using Kepler's third law, and eccentricity can be obtained using the orbit trajectory equation. Then, the apocenter distance can be calculated also using the orbit trajectory equation, with theta equal to 180 degrees. The reconstruction starts off by calculating the excess velocity, and will be calculated using the equation that states that the absolute velocity of the MRO with respect to the Sun is the sum of the absolute velocity of Mars with respect to the Sun and the arrival excess velocity. As the semi-major axis and eccentricity uh, of the heliocentric trajectory is already known, then using the Visify integral, the absolute velocity components in radial and tangential direction can be obtained for both the MRO and Mars velocity components. After that, to, to obtain the arrival excess velocity, uh, it can be done by calculating the difference of the two absolute velocities in vector form, resulting in the excess velocity also in vector form. Then by calculating its magnitude from the vector form, the excess velocity can be obtained to be around 2.35 kilometers per second. The obtained excess velocity is then used to calculate the characteristic energy, which is defined as the square of the excess velocity, and it can also be used to calculate the hyperbolic escape trajectory semi-major axis using the Visify integral. After obtaining the required orbital parameters, then to calculate the change in velocity needed to change the hyperbolic orbit into the elliptic orbit, then it is done by finding the difference between the elliptical orbit velocity and hyperbolic orbit velocity, both at the pericenter. Therefore, it is obtained that the change of velocity needed is around negative 0.74 kilometers per second. The result is negative because slowing down the MRO will need a velocity in the opposite direction of where it is heading. And by using the change of velocity and Tsiolkovsky's rocket equation, the fuel needed for the orbit change are obtained to be around 420 and 42 kilograms. Then, by restating the values of velocity change from a hyperbolic orbit into the initial elliptic orbit and the fuel needed, then comparing it to the real mission data, it can be seen that there is significant error in both results. And the probable causes are the same reasons that is to be said for the deviation in velocity change, which are the point where the MRO arrives at Mars will not necessarily be the pericenter of the orbit, and also the neglectment of drag and influence of Mars. Meanwhile, the possible causes of error in fuel mass calculations is also similar to that of the hyperbolic escape trajectory, such as the impulse data uses its nominal value, the burn used in the assumption is impulsive, and also neglecting drag and maneuvers. But with the addition of the assumption of only using a single burn to enter Mars' initial orbit is quite hard to achieve in the real condition, as its arrival and transfer will need constant attention and correction so that the MRO will reach its desired target as planned. Okay, to conclude this presentation, there are some highlighted parameters which are the total values of the variables from its transverse process, meaning from the escape of the MRO from Earth until its arrival at the initial orbit at Mars. The variables depicted are the transfer time, velocity change, and the total need of propellant mass. And the table depicts that the only variable which has a lower degree of error is the transfer time, while the rest show significant error that comes from the assumptions that deviates from its real condition. And that is the end of my presentation of my reconstruction of Mars Reconnaissance orbiter mission, and thank you for listening.